From far enough away, Earth still looks like Earth. A pale blue bead hung in a black, so deep it feels older than time. A world wrapped in cloud swirls, edged with the silver glint of sunlight. The continents are there, but they are not the ones we know. Coastlines have migrated like living things. Mountain ranges have risen and sagged into quieter shapes. Even the familiar browns and greens have changed their distribution, as if the planet has been slowly repainting itself with a hand too patient for any human eye to catch. If you could stand at that distance and watch the years pass in seconds, you would see the truth about the future. It does not arrive like a catastrophe. It advances like weathering, like rust, like the growth rings inside a tree. 1 billion years is not a chapter in Earth's story. Or it is an era long enough for the planet to reorganize itself from the inside out. And yet, the most important change begins with something so constant that it is easy to mistake it for permanence. The sun, not in the dramatic sense of a sudden flare or an explosion. The star will still rise in the east and set in the west, day after day, for longer than any civilization could ever keep track of. But the sun is not a fixed lamp. It is a furnace balanced delicately between outward pressure and inward gravity, and its brightness shifts as its inner chemistry evolves. Deep in its core, hydrogen nuclei combine into helium. Helium is heavier, and over time it accumulates, subtly changing the core's structure. Models of stellar evolution indicate that this process makes the sun steadily more luminous as it ages. It is a slow drift, and measured not in days, but in hundreds of millions of years, a quiet tilt in the energy budget of the entire solar system. In 1 billion years, that drift is no longer a footnote. The sunlight reaching Earth is stronger than it is now, and stronger here does not mean merely brighter skies. It means more energy entering the climate system, more heat available to push water into vapor, more momentum behind every feedback loop that amplifies warmth. Earth's climate has always been a negotiation between incoming sunlight and the planet's ability to shed heat back to space. With a brighter sun, the terms of that negotiation change. At first, the shift is deceptively ordinary. The tropics grow a little more humid. Heat waves stretch longer. Regions that once lived on the edge of drought find that edge moving inward, year after year, century after century, until maps of habitability become unrecognizable. The poleward reach of warm climates advances, not because the poles forget how to be cold, but because the entire planet is receiving more energy. Ice that once returned faithfully each winter struggles to recover. Snow lines climb mountain sides. In places where glaciers once carved valleys, bare rock begins to appear, dark, heat-absorbing, eager to accelerate the thaw. But the real story is not just temperature, it is chemistry. Earth's atmosphere is not merely a mix of gases. It is an active participant in geology and life, a thin, reactive skin that mediates the exchange between the deep planet and the living surface. One gas, in particular, matters disproportionately to climate: carbon dioxide. It is present in small quantities compared to nitrogen and oxygen, but it plays an outsized role in trapping heat because its molecules absorb and re-radiate infrared energy that would otherwise escape to space. Carbon dioxide on Earth is regulated by an ancient partnership between rock, water, and tectonics. Volcanoes and mid-ocean ridges release carbon dioxide from the interior. Rain, carrying dissolved carbon dioxide, reacts with silicate rocks at the surface. This chemical weathering turns minerals into dissolved ions that rivers carry to the sea, where they can form carbonate sediments. Over geological time, those sediments can be buried, carried downward by subduction, and returned to the atmosphere through volcanic outgassing. It is a planet-sized thermostat, slow but resilient, with the kind of stabilizing mechanism that has helped keep Earth's surface temperate for billions of years despite changes in solar brightness. But the thermostat depends on a fragile premise, that the planet can keep its cycles in balance. When the sun grows brighter, it does not simply heat the air, it accelerates the hydrological cycle. Warmer temperatures increase evaporation from oceans and lakes. More water vapor enters the atmosphere. Water vapor itself is a greenhouse gas, and its increase amplifies warming in a self-reinforcing loop. More heat leads to more vapor traps more heat. At the same time, warmer conditions tend to increase rainfall intensity in many regions, pushing more water through soils and across rock surfaces. And that matters because weathering is not just erosion, it is chemical attack. When the more water circulates, the more rock is exposed to reactive fluids. The faster chemical weathering proceeds, the more carbon dioxide is drawn out of the atmosphere and locked into minerals. This is where the future becomes counterintuitive. A brighter sun warms Earth, but the geochemical response can, for a time, reduce atmospheric carbon dioxide, weakening one greenhouse mechanism even as water vapor strengthens another. Earth begins to drift into a new state, not simply warmer, but chemically transformed. An atmosphere with less carbon dioxide than the biosphere is accustomed to, under a sun that is offering the planet more energy than it knows how to safely dissipate. Over very long time scales, that decline in carbon dioxide has consequences that arrive first as ecological stress, then as collapse. And plants do not eat sunlight in the way popular metaphors suggest. They use light to drive a chemical process that takes carbon dioxide from the air and turns it into sugars, the building blocks of tissues and the fuel for growth. But plants also use those sugars to power their metabolism, releasing carbon dioxide back into the air. When carbon dioxide levels are high enough, photosynthesis outpaces the plant's internal carbon-burning metabolism, and the plant grows. When carbon dioxide levels drop too low, there comes a point at which the plant is effectively treading water energetically. Growth slows, reproduction falters, survival becomes harder in the face of heat, drought, pests, and competition. The biosphere, seen from space, is not a static green coating. It is a delicate system that has co-evolved with the atmosphere that surrounds it. Change the chemistry of the air slowly enough, and life adapts in steps. Change it far enough, and entire metabolic strategies become unviable. In the 1 billion-year world, Earth's surface ecosystems are caught between two pressures that converge like closing jaws. Heat is rising because of the brighter sun and the increasing greenhouse effect of water vapor. Carbon dioxide is falling because warm, wet conditions accelerate the chemical reactions that remove it from the atmosphere. Plants find themselves trying to photosynthesize in air that contains less of their raw material, while enduring higher temperatures that increase their water loss and metabolic costs. The first great transformation of this future Earth is not an asteroid impact, not a volcanic apocalypse, not an instant extinction. It is an attrition, a slow subtraction of complexity from the surface biosphere. Forests begin to retreat from regions that no longer offer them a reliable balance of water and carbon dioxide. The kinds of plants that once built towering canopies yield ground to species with different strategies. Plants that can tolerate drought better, plants that can capture carbon dioxide more efficiently, plants that can survive on thinner margins. But adaptation has limits, and those limits are not moral failings. They are chemistry and physics. Meanwhile, the planet beneath those ecosystems continues its own long, relentless motion. Earth's continents will not stay arranged as they are. Plate tectonics is the reason continents exist as continents rather than a single uniform crust. The lithosphere, the rigid outer shell of the planet, is broken into plates that move slowly atop the softer mantle below. They collide, pull apart, and slide past one another. Oceanic crust forms at spreading ridges and is recycled into the mantle at subduction zones. Mountain ranges rise where plates meet, and erosion wears them down. Over hundreds of millions of years, the continents drift into new configurations, sometimes gathering into supercontinents, sometimes dispersing again. A billion years from now, the exact arrangement is uncertain. It depends on how plate boundaries evolve and how mantle convection patterns shift. But what is clear is that the map will be foreign. Entire seas will have opened and closed. Mountain belts will have been born and eroded into long, subdued scars. Coastlines will have redrawn themselves so completely that the outlines we now recognize would feel like ancient myths. And geography matters because climate is not just about global averages, it is about circulation, how oceans and air currents move heat around. The positions of continents control ocean gateways. They shape the flow of warm and cold water. They determine where deserts form, where monsoons occur, where ice can accumulate. In a warmer world, with different continental arrangements, Earth's climate patterns will reorganize, creating new zones of habitability and new zones of lethal heat. The oceans, for much of this period, still cover the planet. They are not yet gone. They still absorb heat, transport energy, and moderate extremes. They still breathe through their currents, bringing oxygen to depths where life depends on it. But the ocean is not a passive reservoir. It responds to warming in ways that can quietly undermine its own stability. Warmer surface waters tend to stratify the ocean, creating a sharper boundary between the warm, buoyant top layer and the colder, denser water below. When stratification strengthens, it becomes harder for oxygen from the atmosphere to reach deep waters. Mixing slows. The deep ocean can become more stagnant, and in some scenarios, oxygen-poor zones expand. Marine ecosystems can be stressed not only by heat, but by changes in oxygen availability and nutrient cycling, by altered currents and shifting chemistry. The sea, like the land, begins to simplify. Above it all, the sky changes too, in a way that is both obvious and deceptive. As temperatures rise, the atmosphere holds more water vapor. Clouds may become thicker in some regions, reflecting more sunlight back to space and offering a temporary counterbalance to warming. But clouds are notoriously complex. Their net effect depends on altitude, thickness, droplet size, and coverage patterns. Some cloud changes cool, others warm. In climate models of far future Earth, cloud feedbacks introduce real uncertainty. This is one of those places where responsible scientific storytelling must admit what it does not know. The broad direction, greater solar input, warmer conditions, a more vigorous water cycle is robust. The details of cloud response are less certain. Yet even with those uncertainties, the long arc points toward a planet that is inching closer to a threshold, a state in which oceans begin to lose the struggle against evaporation. Imagine Earth under a brighter sun, with surface temperatures creeping upward, and consider what water does when heated. Evaporation increases. More water enters the atmosphere. Rainfall patterns shift, but evaporation continues to climb. Over long enough time, the planet can enter a humid regime in which the upper atmosphere becomes wetter than it is now. This is not just a matter of sticky air at ground level. It is a structural change in the atmosphere's vertical profile. High above the surface, sunlight can break apart water molecules. Hydrogen, the lightest element, can escape to space more readily than heavier gases. If enough water vapor reaches those high altitudes, the planet can begin to slowly lose its ocean, molecule by molecule, in a process that is irreversible on human timescales. Well, this is not yet the full runaway greenhouse state, the kind of catastrophic warming that turns an ocean world into a Venus-like furnace. It is something subtler, a gradual leakage of hydrogen, a slow depletion of a resource that life takes for granted. Models indicate that under a brighter sun, Earth is likely to move in this direction, even if the precise timing depends on atmospheric dynamics, cloud behavior, and geochemical feedbacks. It is here at the 1 billion year mark that Earth's future acquires its particular tension. The planet is still recognizably habitable in some regions, but the boundaries are tightening. Life is still present, but it is being nudged into narrower corridors. The ocean still exists, but it is becoming harder to keep it stable. The atmosphere still supports complex ecosystems, but the ingredients those ecosystems rely upon are being depleted or rearranged. If you could walk on that future Earth, you might find places where life clings on in stubborn abundance. Coastal zones with moderating sea breezes, highlands that still offer cooler temperatures, regions where local conditions preserve moisture. But you would also find expanding belts of harshness, interiors that bake under relentless sunlight, landscapes where vegetation thins and soils degrade, coastlines where the sea retreats from once fertile plains. And the most haunting part is that, from day to day, it would not feel like an apocalypse. The sun would rise, winds would move, storms would still build and break. The planet would still have weather, still have seasons, still have sunsets that can make even a dying world look beautiful. The catastrophe is written not in a single day, but in the direction of change. Because as carbon dioxide continues to fall and the sun continues to brighten, the stress on photosynthesis does not remain a local problem. It becomes the central bottleneck of the biosphere. The energy that fuels almost all complex life is captured first by plants and algae. If that capture slows, everything above it starts to starve. Insects, fish, grazers, predators, decomposers, entire food webs built on invisible chemical transactions between sunlight and carbon. So in the next stretch of this documentary, Earth's future is no longer about rearranged continents or hotter summers. It becomes about the planet losing the very metabolic engine that painted it green in the first place. A slow suffocation of living systems that begins with chemistry and ends with silence. There is a moment in Earth's deep future when the sky still looks normal, yet the air itself has become subtly wrong for the world it once sustained. Not poisonous in the immediate sense, not a choking miasma that kills in minutes. The atmosphere is still mostly nitrogen, still carrying oxygen, still supporting clouds and winds and the restless motion of weather. If you breathed it, you might even survive. But for plants, and for the ecological architecture built upon them, The change is like removing a key ingredient from a familiar recipe and expecting the meal to taste the same. Life's surface machinery was tuned over eons to a certain range of carbon dioxide, and now that range is slipping away. The problem is not that carbon dioxide disappears entirely. The problem is that it becomes scarce enough that the dominant strategy for capturing it, photosynthesis, as most land plants practice it, begins to fail. On Earth today, many plants use a photosynthetic pathway that works well when carbon dioxide is relatively plentiful and temperatures are moderate. But as carbon dioxide drops and heat rises, those plants are forced into an increasingly expensive balancing act. Their leaves have tiny pores called stomata, valves that open to let carbon dioxide in. When stomata open, water escapes. In a hotter world, water loss accelerates. Plants respond by closing stomata more often to conserve moisture, but that also restricts carbon dioxide intake, starving photosynthesis. Some plants have evolved alternative strategies. Certain grasses and crops use a pathway that effectively concentrates carbon dioxide inside their tissues, allowing them to photosynthesize efficiently even when the air contains less carbon dioxide. But these strategies are not universal. They require anatomical and biochemical adaptations, and they come with trade-offs. You can imagine an ecological filter tightening. In the 1 billion-year world, the planet's surface begins to favor organisms with certain traits, while quietly eliminating others. The first casualties are not necessarily the most fragile-looking plants. They are often the ones most dependent on high carbon dioxide availability and abundant water, the great, lush ecosystems that dominate temperate and tropical regions in our time. Forests that once acted as planetary lungs, drawing carbon from the air and exhaling oxygen, begin to lose ground. Tree lines retreat, canopies thin. Insects that specialized in those forests struggle. Birds that nested in them disappear. The intricate web of mutualisms, plants depending on pollinators, animals depending on fruiting seasons, unravels as the stability of the underlying system falters. In Earth's deep history, mass extinctions have often been painted as sudden events: a meteor, a flood of lava, an abrupt climate shock. But there is another kind of extinction, quieter and arguably more cruel, because it leaves no single moment of impact. It is the extinction of margins, the gradual tightening of tolerances until organisms are no longer outcompeted by rivals, but outcompeted by physics. As carbon dioxide continues to fall, photosynthesis becomes harder not only on land, but in the oceans as well. Marine photosynthesis is carried out mostly by microscopic organisms, phytoplankton, that float near the sunlit surface. They form the base of marine food webs. Their success depends on nutrient availability, light, and the chemistry of seawater, including dissolved carbon dioxide and related carbonate species. In a warmer world, with stronger stratification, nutrient mixing can slow, reducing the supply of key elements from deeper waters. At the same time, changes in atmospheric carbon dioxide influence ocean chemistry, shifting the balance of dissolved carbon forms. The ocean does not lose its primary producers overnight, but the biosphere begins to lean harder on fewer and fewer groups that can tolerate the new conditions. Biodiversity declines. Ecosystems become less resilient to shocks. A planet that was once richly layered with life starts to look, from a biological point of view, more like a set of scattered refuges connected by fragile threads. Now add the other pressure: heat. A brighter sun does not simply raise average temperatures. It increases the intensity of extremes, particularly in regions where geography traps heat and limits moisture, there is a fundamental constraint on animal survival tied to a concept called wet bulb temperature. Wet bulb temperature is a measure that combines heat and humidity, reflecting the lowest temperature that can be reached by evaporating water into the air. It matters because many animals, including humans, cool themselves by sweating or panting by evaporating water. If the air is too humid and too hot, evaporation becomes inefficient. The body cannot shed heat, and internal temperatures rise toward dangerous levels. Even if water is available to drink, the ability to cool can fail. In the 1 billion-year scenario, models suggest that some low-latitude regions may approach or exceed survivable wet bulb thresholds for many large animals, particularly during heat waves. This does not mean every day is lethal. It means that, with increasing frequency, the climate crosses into regimes where being a large, active animal on the surface becomes a liability. In the tropics, the cradle of much of Earth's biodiversity, become less hospitable to complex life, not only because of heat, but because heat arrives together with humidity, the worst combination for an evaporatively cooled body. Life responds by moving. Populations shift toward higher latitudes. They climb toward higher elevations. They retreat into coastal margins where sea breezes moderate temperature, or into forest remnants where shade and transpiration offer microclimates. Burrowing becomes more valuable. Nocturnal lifestyles expand. The rhythm of life changes, becoming more hidden, more constrained, more dependent on small pockets of survivable conditions. Yet even these refugees are temporary, because the underlying trends do not stop. The sun continues to brighten. Weathering continues to draw down carbon dioxide. The planet continues to leak hydrogen to space as the upper atmosphere becomes moister. And as carbon dioxide declines further, there comes a threshold where even the most efficient land plant strategies struggle to maintain net growth. This is where Earth's future begins to resemble a kind of metabolic suffocation. Oxygen itself is not the immediate limitation at first. In fact, oxygen can persist in the atmosphere long after complex photosynthetic ecosystems collapse, because oxygen is chemically reactive but also buffered by the rates at which rocks and gases consume it. What changes first is the biosphere's ability to generate enough new organic matter to sustain complex food webs. Predators find fewer prey, grazers find fewer plants, decomposers find less litter. Nutrient cycles slow as the living component that drives them shrinks. As plant productivity declines, the landscape changes physically. Vegetation stabilizes soils. It anchors riverbanks. It slows runoff. It traps sediments. When vegetation thins, erosion increases. Rivers carry more sediment into the sea. Dust storms become more common over drying interiors. The planet's albedo, its reflectivity, can change as darker forests give way to lighter deserts or bare rock, and that can feed back into climate in complicated ways. In some regions, more reflective surfaces might slightly counter warming. In others, dust in the atmosphere could alter cloud formation and rainfall, potentially worsening aridity. Earth's climate becomes not only hotter, but more chaotic in its regional patterns as the biosphere loses its stabilizing influence. By now, the idea of a habitable Earth becomes misleading if you imagine it as a globally friendly environment. Habitability fractures. It becomes a mosaic of zones that range from tolerable to hostile, separated by gradients that can be crossed only by organisms with the right adaptations or by life sheltered beneath the surface. If you visited this future world, you might still find green, just not the kind of green you recognize. You might see resilient grasses in some regions, specialized shrubs, tough microbial mats in places where water lingers. In coastal and highland refuges, you might find ecosystems clinging to existence like islands in a biological archipelago. But the grand, planet-spanning productivity that characterized much of Earth's recent history has diminished, and the oceans too are changing their identity. The sea's surface is warmer, and as the difference between surface and deep water grows, vertical mixing weakens. In some scenarios, the deep ocean becomes increasingly oxygen-poor. Oxygen-poor conditions favor certain microbes that use alternative chemical pathways to extract energy, pathways that can produce gases like hydrogen sulfide in extreme cases. This does not necessarily mean the entire ocean turns toxic, but it does mean that large portions of marine habitat can become inhospitable to many animals. Reef-building organisms, sensitive to temperature and chemistry, struggle. Fisheries of the future, if anyone were there to name them, would collapse as food webs simplify. At the same time, sea levels are influenced by more than melting ice, which by now may be largely absent. A sea level in deep time also responds to the volume of ocean basins and the dynamics of the seafloor. Changes in tectonics can alter the shape of ocean basins, raising or lowering global sea levels over millions of years. But in the 1 billion-year future, another factor increasingly matters: the slow loss of water itself. As hydrogen escapes to space, Earth's inventory of water shrinks. It is a quiet theft by sunlight, and it is relentless. A shrinking ocean does not disappear evenly. Sea levels fall, exposing continental shelves that once lay underwater. New land appears, flat plains of former seabed, salt-crusted and sun-baked. Coastlines retreat. Shallow seas that once supported rich ecosystems vanish, replaced by arid basins. Ocean currents, already reshaped by continental drift, are further altered as the geometry of the sea changes. The planet's heat transport system becomes less efficient, allowing hotter extremes on land. Here, the story of life's decline and the story of geology become inseparable. Because as oceans retreat and climates dry, the very processes that regulate Earth's long-term stability begin to shift. Chemical weathering depends on water. If the planet becomes drier overall, weathering rates can change. If weathering slows, carbon dioxide might stabilize or even rise relative to the earlier drawdown, depending on volcanic outgassing. But this is not a rescue story. Even if carbon dioxide stabilized, the brighter sun continues to push Earth toward higher temperatures, and the loss of water continues to erode the planet's ability to buffer heat. Moreover, the cycling of carbon between the surface and the interior depends on plate tectonics. Subduction carries carbonates downward. Volcanism releases carbon dioxide upward. If plate tectonics changes, if it slows, reorganizes, or weakens as the mantle cools and the lithosphere thickens, then Earth's carbon thermostat can break or become far less effective. Earth is old. By 1 billion years in the future, it is older still. Its internal heat budget continues to decline. Radioactive elements that generate heat in the mantle decay over time, reducing the energy available to drive convection. Mantle convection is the slow churning that helps move tectonic plates. If convection weakens, plate motion can slow. Subduction zones might become less active. Volcanism could change in style and frequency. The planet's deep engine, which has long recycled crust and maintained a dynamic surface, begins to show signs of fatigue. We cannot say with certainty exactly when Earth's plate tectonics will end, or whether it will end gradually or in fits. The evidence suggests that plate tectonics is sensitive to mantle temperature, water content, lithospheric strength, and the complex physics of rock deformation. But many models and lines of reasoning indicate that, as Earth cools over geological time, it may become harder to sustain the kind of global plate recycling we see today. A planet without active plate tectonics can still be geologically interesting, but it becomes less capable of regulating climate through long-term cycles. It becomes more like a world that locks into a state and stays there. By the late stages of this 1 billion-year trajectory, Earth is not only losing its rich biosphere, it is losing flexibility. This is the turning point of our documentary's logic. In the first section, the brighter sun set the stage, accelerating the water cycle and drawing down carbon dioxide. Now we see the biosphere reacting, retreating, simplifying, suffocating as its metabolic foundation erodes. But the next step is deeper, more structural. As surface conditions change, they feed back into the planet's geology. As water becomes less abundant at the surface, and as the interior cools, the machinery of plate tectonics may weaken. And when that happens, Earth's future stops being merely a warmer version of itself. It becomes a different kind of planet. The question is not only what happens to forests, oceans, and animals. The question is what happens to a world when the system that renews its face, when the planet's ability to recycle and reinvent its crust begins to fail. Because once Earth starts to lose that deep dynamism, the surface no longer has an internal partner strong enough to counter the sun's slow, tightening grip. And that is where we are heading next, toward a planet whose seasons may still turn, but whose geology is beginning to fall silent. A world slowly locking itself into a dry, rigid future. By the time Earth reaches this stage of its future, the planet has begun to feel less like a living system and more like a mechanism running out of tolerance. Not because motion stops. Continents still creep. Storms still form. The ocean, though diminished, still heaves in long, slow swells. But the most profound movements on Earth have always happened out of sight, under pressures and temperatures so extreme that rock behaves like something between a solid and a fluid. That hidden motion is what has kept the surface young. The slow churn of the mantle, the recycling of crust, the continuous rebuilding of landscapes. When people speak about plate tectonics, they often picture dramatic moments, an earthquake, an eruption, a mountain rising. But plate tectonics is really Earth's long-term metabolism. It is how the planet ventilates heat. It is how it refreshes its skin. It is how carbon travels between the sky, the sea, and the deep interior. And it is tightly linked to something that the 1 billion-year Earth is beginning to lose: water. Water is not just a surface feature. It is a geological lubricant and a chemical catalyst. At subduction zones where one plate dives beneath another, water carried down in oceanic crust helps weaken minerals and lower the melting point of rocks, making it easier for slabs to sink and for magma to form. Water helps sustain the very processes that keep plates moving. As the surface dries and the oceans retreat, less water is available to be cycled into the mantle. The crust becomes drier, stronger, more resistant to bending and breaking. Subduction becomes harder to initiate and harder to maintain. At the same time, Earth's interior is cooling. This is not speculation, it is an inevitability. Earth formed hot, and for billions of years it has been losing heat to space. Some heat is generated by the decay of radioactive elements in the mantle and crust. But those radioactive sources diminish over time. With less heat to drive convection, the mantle's slow circulation can weaken. Plates may still move, but the engine behind them becomes less vigorous. Over very long time scales, that can change the style of tectonics, turning a dynamic planet into one that behaves more like a rigid shell. We cannot pinpoint the exact moment when Earth's plate tectonics would stall, because the system is complex and sensitive to the evolving strength of the lithosphere and the distribution of heat inside the mantle. But the trend is clear. A cooling interior and a drying surface are both forces that push Earth toward a more stagnant future. If plate motion slows, the consequences unfold in a chain that touches almost everything. First, mountain building becomes rarer. Collisions still happen, but less frequently or less intensely, and once formed, mountains face an opponent that never sleeps: erosion. Rain, wind, and gravity will keep grinding high terrain down. Over millions of years, rugged landscapes smooth into broad uplands and gentle ranges. The planet's topography becomes less dramatic, not because it is dead, but because it is no longer being renewed fast enough to replace what erosion removes. As relief diminishes, so does the variety of climates. Mountains create rain shadows, guide winds, generate diverse habitats across altitude gradients. A flatter world has fewer of those contrasts. It is easier for heat to dominate. It is easier for dryness to spread. Second, volcanism changes. Volcanoes are one of the main ways Earth releases gases from its interior, including carbon dioxide and water vapor. Not all volcanism depends on subduction. Some occurs at hot spots and spreading ridges. But if plate tectonics weakens overall, the global pattern of volcanism can shift. Fewer subduction zones mean fewer arcs of volcanoes injecting gases into the atmosphere. Spreading ridges, if they slow, create less new seafloor and release fewer volatiles. In the long run, a planet with less volcanic outgassing becomes less able to replenish atmospheric carbon dioxide once weathering has drawn it down. This is where the story loops back on itself with a kind of grim elegance. The brightening sun pushed Earth toward warmth and toward carbon dioxide loss. The biosphere contracted as carbon dioxide fell. Now, the weakening of tectonics threatens to remove one of the planet's few natural ways to restore carbon dioxide to the air. The thermostat that once steadied Earth begins to seize. Yet even here, the future refuses to be simple. As Earth dries, chemical weathering can slow because water is essential to those reactions. Less rain, fewer rivers, and more arid landscapes can reduce the rate at which carbon dioxide is pulled from the atmosphere by rock. That could, in principle, allow carbon dioxide to stabilize at some low level rather than falling indefinitely. But stabilizing at a low level is not a return to a lush world. Under a brighter sun, low carbon dioxide does not bring back temperate climates. It just changes the balance of heat trapping. And with less water in circulation, the biosphere cannot regain its former breadth. The planet's limiting factor shifts from carbon alone to water and heat together. The geography of this future Earth is also reshaping the climate in its own way. Over 1 billion years, continents are likely to gather and separate in large-scale cycles. Many models and reconstructions of Earth's past suggest that supercontinents form intermittently when drifting land masses converge into a single enormous assembly. Whether Earth will form a new supercontinent within exactly 1 billion years is uncertain, but the possibility is plausible enough to matter because of what supercontinents do to climate. A supercontinent creates a vast interior far from the moderating influence of oceans. Even on today's Earth, continental interiors experience more extreme seasonal swings than coastal regions. On a hotter planet with shrinking seas, those interiors become punishing. Moisture struggles to penetrate. Rain falls in bursts at the margins, while the center dries into a world of heat, dust, and salty basins. River systems that once crossed continents can shrink or vanish, replaced by episodic floods that carve dry channels and then disappear into the ground. If the oceans have retreated, the effect intensifies. Shallow seas are powerful climate moderators. They store heat and release it slowly, feeding clouds and rainfall. When those shallow seas are gone, the surface becomes more exposed, more prone to extremes. The same sunlight that once evaporated ocean water into rain now strikes bare ground and salt flats, driving temperatures higher in the day and allowing stronger cooling at night, because dry air holds less heat. In such a world, season begins to mean something different. Seasons, as we experience them, are controlled mainly by Earth's axial tilt, the angle at which the planet's spin axis leans relative to its orbit around the Sun. That tilt is not perfectly fixed. It wobbles slightly over time due to gravitational interactions, and the Moon plays a stabilizing role by damping the more chaotic swings that could otherwise occur. Over hundreds of millions of years, the Moon is slowly moving farther away from Earth, carried outward by tidal interactions. In 1 billion years, it will likely be tens of thousands of kilometers more distant than it is now. What that means for Earth's tilt is uncertain. Some models indicate that without the Moon's stabilizing influence, Earth's axial tilt could vary more dramatically, potentially leading to extreme seasonal changes over long periods. With the Moon still present but farther away, Earth may become somewhat more prone to larger swings than it is today, though it may not become fully chaotic. It is one of those places where we can sketch the physics, but should be honest about the range of outcomes. Still, even without a dramatic change in tilt, the lived experience of seasons on a 1 billion year Earth could fade in many regions for a simpler reason. Heat becomes the dominant condition. When a climate sits close to the limits of biological tolerance, the difference between summer and winter is no longer a gentle rhythm. It becomes a narrow window of relative survivability, punctuated by long stretches of stress. In some low-latitude regions, the year may feel like variations on one theme, hot, because even the coolest months do not bring relief. In other regions, especially at higher latitudes, the seasonal cycle may still exist, but it plays out on a planet whose baseline has shifted so far toward warmth and dryness that the old meanings of spring and autumn no longer apply. Time itself is changing too. Earth's rotation is gradually slowing because tidal friction transfers rotational energy into heat and pushes the Moon outward. The day lengthens over geological time. The exact rate has varied across Earth's history, and it depends on the configuration of continents and oceans because tides are shaped by basin geometry. Over 1 billion years, the day may become several hours longer than it is now, though the precise value is uncertain. A longer day means longer heating under sunlight and longer cooling at night, increasing daily temperature swings, especially over dry land. In a desertified world with fewer clouds and less humidity, those swings can become harsh. Daytime surfaces that sear, nights that cool quickly, stressing any organisms still exposed to the open air. All of this is taking place under another, quieter transformation. The planet is becoming more rigid. As plate tectonics weakens, Earth begins to resemble what planetary scientists call a stagnant lid world, a planet where the outer shell behaves as a single, mostly unbroken layer rather than a set of mobile plates. Venus appears to be such a world today. Mars, largely geologically quiet, is another example of a planet whose early dynamism faded as its interior cooled. Earth would not become a perfect analog of Venus or Mars because its mass, internal composition, and history are different. But the direction, toward less recycling, less resurfacing, fewer global-scale renewals, is a genuine possibility as Earth ages. If Earth's tectonics enters a stagnant lid regime, it does not mean all volcanism ends. Heat can still escape through hot spots, through occasional plumes, through fractures forced by internal stress. But the pattern becomes less like a planet-wide conveyor belt and more like a set of isolated leaks. The surface becomes older on average. Craters from impacts, once erased quickly by tectonics and erosion, can persist longer. Deserts can sit in place for ages, their dunes migrating but their basins remaining. The planet begins to keep its scars. There is a certain kind of silence that settles over a world when its geology quiets, and it is not the silence of stillness. It is the silence of repetition. Weather keeps moving the same dust around. Rare rains carve familiar channels and then vanish. Without ongoing uplift, rivers lose their steep gradients. They meander lazily, depositing sediment rather than cutting into fresh rock. Nutrients that once came from the continual exposure of new minerals become harder to access. In the long run, this matters for life, because ecosystems depend not only on sunlight and water, but on elements like phosphorus, which are supplied by the breakdown of rock. A geologically tired planet can become biologically impoverished simply by starving the surface of essential ingredients. And now, there is another shield that may begin to weaken: the magnetic field. Earth's magnetic field is generated by the motion of liquid iron in its outer core, driven by heat flow and compositional changes as the inner core grows. The field protects the atmosphere to some extent by deflecting charged particles from the solar wind. A strong magnetic field does not make atmospheric loss impossible, but it can reduce certain pathways by which the upper atmosphere is eroded. Whether Earth's magnetic field will still be strong in 1 billion years is uncertain. The core will continue to cool, and the geodynamo depends on the details of that cooling and the growth of the inner core. Some evidence suggests Earth's dynamo could persist for a long time, potentially billions of years, but its intensity and stability could change. If the field weakens significantly, the upper atmosphere could become more vulnerable to solar wind stripping, especially in a future where the upper atmosphere is already wetter and hydrogen escape is already an issue. Again, and this is not a single catastrophic flip, it is a gradual increase in vulnerability, a little more atmospheric loss here, a little more ionization there, a little more of Earth's remaining water and lighter gases being nudged away by the steady pressure of sunlight and solar wind. By the end of this section of our documentary, Earth has crossed a psychological boundary, not an official line drawn by scientists, not a neat threshold with a name, but a shift in character. The planet is drying. The biosphere is thinning. The deep recycling engine that once kept continents in motion and climates buffered is slowing, perhaps faltering. Geography may be converging into configurations that intensify aridity. Days are longer, swings harsher. Even the planet's invisible shields may be changing, and yet the world is not empty. Life has not vanished. It has simply been forced into a different relationship with the surface. The familiar richness of forests and diverse oceans has narrowed, but the Earth still offers niches, places where water persists, where temperatures are tolerable, where chemistry still allows metabolism. The next question is where those niches are, and what kind of life can hold them. Because as the open-air biosphere continues to collapse, survival becomes a matter of retreat, into altitude, into latitude, into rock, into salt, into darkness. The surface we think of as Earth begins to look increasingly like an exposed skin over a hidden world of last habitats, and that is where we go next, to the final refuges and to the quiet after. In the end, Earth does not die everywhere at once. 1 billion years from now, on the planet's surface is not a uniform wasteland. It is a patchwork. Sun-struck deserts, salt flats where shallow seas once lay, highlands that still catch cooler air, polar margins that have become the last broad sanctuaries from relentless heat. If you could fly above it, you would see a world that still has weather but fewer colors, fewer greens, fewer deep blues, more muted browns and bleached mineral tones, as if the planet has been left too long under a harsh lamp. The most haunting part is how ordinary much of it can look from moment to moment. A wind lifting dust into a pale curtain, a storm line marching across a horizon, a sunrise turning clouds gold. Beauty does not require abundance. Even a world in decline can stage a sky that makes you forget briefly what is being lost. But down at ground level, the reality is harsher. The future Earth is a planet where heat and dryness have become the dominant architects, reshaping ecosystems not by dramatic blows, but by shrinking the narrow band of conditions in which complex life can function. The broad trajectory is driven by 3 intertwined forces. The first is the brightening sun, continuing its slow increase in luminosity. The second is the planet's changing atmosphere, its carbon dioxide drawn down by long-term geochemical processes and no longer buffered as effectively by a weakening tectonic cycle. The third is water loss, the gradual escape of hydrogen to space as the upper atmosphere becomes wetter and sunlight breaks water molecules apart. None of these forces is speculative on its own. The uncertainty lies in their timing, their interactions, and the exact pathways Earth takes through the space of possible climates. But the destination they point toward is consistent, a surface increasingly hostile to the rich, open-air biosphere we know. In that future, life survives where physics allows. To understand those refuges, you have to think less like a gardener and more like a field geologist. Life does not need forests or coral reefs as concepts. It needs gradients, places where energy flows and chemistry remains usable. It needs liquid water, even if only intermittently. It needs stability long enough for reproduction. It needs, above all, a way to avoid being cooked by sunlight and humidity. On a hotter Earth, the easiest way to do that is to leave the open air. The ground becomes shelter. Rock is insulation. Soil pores and cracks in bedrock hold moisture longer than the surface does. A few meters below ground, temperature swings soften. In some terrains, groundwater can persist even when rivers and lakes vanish, stored in aquifers like hidden seas. The deeper you go, the less you care about the scorching day and the freezing night. The planet's surface becomes an abrasive skin over a buffered interior. Microbial life? Organisms too small to see, too simple to need oxygen-rich air or abundant food webs, has always been Earth's most durable form of biology. For most of Earth's history, microbes dominated. Even today, they inhabit extremes that seem incompatible with life. Hot vents, frozen deserts, acidic pools, deep rocks. In the 1 billion-year world, microbes are not a footnote. They are the main characters. Some refugees are obvious. The polar regions for a long time remain cooler than the rest of the planet. Even as global temperatures rise, high latitudes can preserve lower summer peaks simply because the sun's angle is lower and because long winter darkness still exists. But the poles are not immune. As ice vanishes and oceans retreat, the moderating influence of nearby water can diminish. Still, compared to equatorial deserts, the poles offer a slower collapse, a longer runway for life. High altitudes are another refuge. Mountains, even on a planet with less active tectonics, do not vanish overnight. Elevated plateaus and remnant ranges can continue to create cool microclimates. Air pressure is lower at altitude, and temperatures tend to decrease with height. These places can act like climatic lifeboats, especially if they intercept moist air and generate pockets of rainfall or snowfall. The irony is sharp. In a world where the biosphere has shrunk, the last robust ecosystems may cluster around ridges and peaks, not because those places are especially fertile, but because they are merely tolerable. Coasts also matter, as long as oceans remain. Even a reduced ocean can moderate temperature swings. Sea breezes bring relief during the day. Coastal fogs can deliver moisture in the form of condensation rather than rainfall. In a future where rivers are fewer and drought dominates interiors, these thin veils of fog can be the difference between sterility and a narrow ribbon of life. But the deepest refuges, the ones that can persist through the worst phases, are not the ones you can see easily from above. They are subterranean and chemical. In salty basins where water evaporates and leaves behind concentrated brines, you find one of the strangest properties of water. Salt lowers its freezing point and changes its behavior. Briny solutions can remain liquid under conditions where fresh water would evaporate or freeze. In today's world, microbes known as halophiles thrive in salt-saturated environments that would dehydrate most life. In the future, Earth's shrinking seas and expanding salt flats, brines may become common in isolated pockets. They are harsh, but harsh does not mean lifeless. It means selective. In rocks, deep underground, you find another type of life support system, chemical energy. Even without sunlight, microbes can survive by using chemical gradients created when water interacts with minerals. When certain rocks react with water, they can produce hydrogen and other molecules that microbes can use as fuel. This kind of metabolism exists today in deep subsurface environments. In a future where surface photosynthesis is crippled, such chemical ecosystems become disproportionately important. Life retreats into the planet's pores and fractures, living off the slow reactions between water and stone. If you stand back and consider what this means, it is almost poetic in its reversal. Life began on Earth in a world that was once hostile, likely dominated by microbes in oceans and hydrothermal systems. Over billions of years, it expanded outward, painting continents green, filling skies with oxygen, building complex animals and plants. Now, under a brighter sun, the biosphere contracts inward again, returning to the deep and the hidden. Surface animals, if any remain at all, become specialists in avoidance. Large-bodied creatures are most vulnerable to heat because they generate and retain more internal heat. Small creatures can hide in burrows, shelter under rocks, emerge at night, and survive on minimal resources. If complex animals persist, they are likely small, nocturnal, and adapted to extreme scarcity. The world becomes less a stage for large, visible life, and more a planet of quiet movement at the margins. Insects, small reptiles, perhaps sparse vertebrates, in the coolest refuges, each living in a narrow band of conditions that shifts year by year. But even that stage may not last. As water loss continues, the oceans keep shrinking. Eventually, a tipping point approaches where the remaining surface water can no longer maintain a stable, long-term hydrological cycle. When the ocean becomes too small, evaporation and precipitation patterns change fundamentally. The atmosphere may carry less moisture overall because there is less reservoir to evaporate from. The climate becomes drier, with fewer clouds and less rainfall. Without enough water vapor to form clouds, more sunlight reaches the surface, heating it further. The deserts widen, the last lakes become seasonal, then ephemeral, then vanish. At some point, the idea of surface rivers becomes rare. Instead of flowing systems that connect continents to oceans, you have isolated drainage events after rare storms, flash floods that carve channels and then disappear. The planet's surface begins to resemble the dry channels and ancient lake beds seen on Mars today, except this is Earth, and the channels are still active occasionally. Like faint echoes of a wetter past, the atmosphere changes again in response. With less surface water, the upper atmosphere may become less wet, potentially slowing hydrogen escape. But by this stage, a great deal of water may already be gone. Earth's remaining water inventory is reduced. The ocean is smaller. The deep cycles that could replenish surface water are limited because much of Earth's water is locked in minerals and the mantle, and the pathways that exchange it with the surface depend on tectonics and volcanism. If volcanism continues in isolated regions, it may release some water vapor and carbon dioxide, but without an active global recycling system, these injections are episodic. They may create temporary climate pulses, brief intervals of slightly altered atmospheric chemistry. But these are ripples against a long trend, increasing solar brightness and decreasing surface water. And then there is the question of oxygen. Oxygen in Earth's atmosphere is a product of photosynthesis on geological timescales. Without substantial photosynthesis, oxygen will gradually decline as it reacts with rocks, volcanic gases, and reduced minerals. The timescale is long. Oxygen does not vanish overnight, but over millions of years, as surface productivity collapses, oxygen production falls below oxygen consumption. The atmosphere begins to lose its oxygen richness, drifting toward a state that would feel alien to any creature evolved under today's skies. As oxygen declines, the window for animals narrows further. Complex aerobic metabolism depends on oxygen. If oxygen drops low enough, only organisms with alternative metabolic pathways can persist easily. Microbes that use anaerobic processes, metabolisms that do not require oxygen, become more dominant. At this point, Earth is still a planet with life, but it is no longer the kind of life that announces itself loudly. It is not a world of forests seen from orbit, not a world of plankton blooms coloring oceans, not a world of complex animal migrations and seasonal explosions of growth. It is a world where life is mostly microscopic, mostly hidden, mostly clinging to the last places where water and chemical energy still meet. If you could look at Earth from afar with an instrument sensitive to the planet's atmospheric signature, you might notice something else. The biosignatures would weaken. A living planet can leave clues in its atmosphere, but gases that coexist in ways that are hard to maintain without biology. Oxygen alongside methane, for example, can be a hint, because these gases react and should not persist together without constant replenishment. On a future Earth, with diminished photosynthesis and declining oxygen, these kinds of signals could fade. From the perspective of a distant astronomer, Earth might begin to look less obviously alive, even if microbes still inhabit its subsurface. The planet's shout becomes a whisper. This is a sobering thought for our search for life elsewhere. It suggests that a planet can be inhabited, yet appear sterile from a distance, depending on where its life is and how energetically it is interacting with the atmosphere. Earth's own future may become a lesson in cosmic ambiguity. And beyond the biology, the planet's face continues to change. Without active plate tectonics reshaping continents, the surface becomes progressively older. Impact craters remain longer. Volcanic plains, if they form, can sit undisturbed for immense spans of time. Erosion continues, but with less rainfall and fewer rivers, erosion becomes more episodic and wind-driven. Sand seas expand. Dust becomes a defining feature of the planet, carried high into the atmosphere during storms and then settling in quiet layers across basins. The sky itself may be hazier at times, the sun dimmed behind suspended particles. In a dry world, dust plays a role similar to aerosols in our current atmosphere, scattering sunlight and influencing cloud formation. The climate of such a planet can oscillate between clearer, hotter periods and dustier, slightly cooler intervals, though the overall trend remains one of increasing heat and decreasing water. If you stood on the ground in the late afternoon, you might see the sun as a harsh, white disk, its light less softened by moist air. Shadows could be sharp. The horizon might shimmer with heat. At night, the sky could be brilliant with stars, because a drier atmosphere can be clearer, and clouds are rarer. The Milky Way would arch overhead, indifferent. It would be a world of wide silence, not because wind and weather have stopped, but because the familiar sounds of life are gone. No dense chorus of insects in summer forests, no layered calls of birds at dawn, no amphibians near water, because water itself is a rarity. The soundtrack of Earth, the one we have always known, is replaced by simpler sounds: wind, dust, occasional thunder, and the crack of cooling rock. And yet, the story does not end with a dead planet. It ends with a planet that has changed its mode of being. Earth began as a molten world, cooled into oceans, nurtured life, built an atmosphere rich in oxygen, and maintained a dynamic crust for billions of years. In 1 billion years, it is still evolving, still active, still responding to the inexorable physics of a brightening star. But its surface has moved beyond the era where complex, open-air life can easily thrive. If there is a lesson here, it is not that Earth is fragile in the way a glass is fragile. Earth is resilient on planetary timescales. It survives impacts and ice ages, continental collisions and mass extinctions. It is not easily destroyed. But habitability, the specific narrow band of conditions that allows forests, oceans full of fish, and creatures that breathe oxygen, habitability is more delicate. It depends on balances, on feedback loops that must stay within limits, on a star that must not get too bright, on a planet that must not lose its water, on cycles that must keep carbon and nutrients moving. 1 billion years from now, those balances are likely to have shifted past the point where Earth can sustain the kind of biosphere we recognize. The planet will still turn, the sun will still rise, but the surface will tell a different story.